Okay. All right, so 2.8 is talking about the derivatives of function. And so there are three definitions to the derivative, and I told you that I would give them to you. These are them. This is the most common one, or this is the one that most of us use. And then the next one that we use a lot is this one. The one that's typically not used is that middle one, but you should know all three of them by heart. I typically at some point in the class ask for these definitions so that you have them down, okay? So you should have those three memorized. Some notation that you guys should know. All of these things that I have written down here are all different examples of a derivative, okay? F prime of x, y prime, dy dx, dy over dx with a function of y, df over dx, just another notation. A capital D with the function is another. And then this last one, our book has it. I don't like it. But I wrote it down so you guys could see it. The reason I don't like it is because in higher level mathematics, that subscript x is called a partial derivative with respect to x. And yeah, I don't want to convolute the notation, okay? But all of these that I've written here are an example of what I could write on an exam to ask you to find the derivative, okay? Now, eventually we'll get into finding the second derivative, and to do that, I could do that by writing y double prime. I could write f double prime of x, or I could do something that looks like this. That is notation for the second derivative, okay? Those are all examples of what the second derivative would look like. And you guys thought that the algebra was busy, right? Carol wrote on there a lot of algebra. This is not a lot of algebra. We're about to start doing some algebra. And when we get to chapter 5, we're really going to start to do some algebra. This right now is just the beginnings of what we're trying to do, okay? So let me show you this one example, and we'll do it. So it's telling us, it says, if f of x is equal to x cubed minus x, find a formula for f prime of x. So we're going to use one of the three definitions to see if we can come up with a shortcut to find the derivative, right? Or to come up with the derivative. So I'm going to use the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay? Now, using that, I'm going to plug in everywhere I see x, I'm going to plug in x plus h. And so I'm going to take the limit as h goes to 0 of x plus h cubed minus x plus h minus x cubed minus x, all of that over h. Are we okay with what I did there? Why is the cube out? Outside of the x plus h. Why is the cube on the outside of that? The reason is because remember, everywhere I see x, so it's x cubed, right? So where it's x cubed, I'm going to make that x become x plus h. And so then that becomes x plus h, that whole quantity cubed. All right, just making sure. There's no problem. Now from here, you guys, it's important that you guys know your expansion. Some of you may try to do your expansion by doing this. And if you're going to do it that way, it's going to take you quite some time. So I hope you guys know how to do your expansion quickly so that you can get what I'm about to get as quickly as I get it. Do you guys agree with my expansion? We're okay? All right. Now what I want to do is I want to work on eliminating some things, right? So the things that are the same that can be eliminated, I see an x cubed. There's an x cubed. It's negative, so they cancel out. I see a minus x and an x, so those go away. And now what I end up seeing is the limit as h goes to 0 of 3x squared h plus 3xh squared plus h cubed minus h all over h. And now we can see each and every one of these terms has an h in it. That's awesome. That's what we want. And so the limit as h goes to 0, I'm going to factor out an h, so I'm going to get 3x squared plus 3xh plus h squared minus 1 all over h. And so that's going to cancel, right? And so I'm going to get the limit as h goes to 0 of 3x squared plus 3xh plus h squared minus 1. And when I apply the limit there, this is going to go to 0 and this is going to go to 0, correct? And so I'm going to end up with 3x squared minus 1. And that is the derivative of x cubed minus x. So do you see how the algebra gets more and more cumbersome? Just wait till we get to the integrals and the definition of the integral. It's going to become quite cumbersome. Are there any questions on the steps that I did in this problem? No? Are you sure? Okay. So in this example now, this is an awesome problem. We're again going to find the derivative of this thing by using the definition. And so again, the limit as h goes to 0 of f of x plus h minus f of x all over h is coming into play. Something that's important in this problem, and it's asking for domain. So the domain of our original function, isn't that going to be x greater than or equal to 0? Yes? Okay. So now when we plug in to do our derivative, it's going to be the square root of x plus h minus the square root of x all over h. Agreed? Right, that's just doing the function notation substitution. Now from here, what did I tell you guys that we should do if we have radicals? Perfect, the conjugate. So then I'm going to take the limit as h goes to 0 of the square root of x plus h minus the square root of x times the square root of x plus h plus the square root of x all over h times the square root of x plus h plus square root of x. Okay? Cool. So then that's going to be the limit as h goes to 0 of x plus h minus x all over h times the square root of x plus h plus square root of x. Agreed? Okay, so then from here, we can clean it up. So the limit as h goes to 0, we're going to have h over h square root of x plus h plus square root of x. The h's will cancel, and so I'm going to have the limit as h goes to 0 of 1 over square root of x plus h plus square root of x. Applying the limit, I'm going to get 1 over square root of x plus square root of x, which will yield 1 over 2 square root of x. That is our derivative. Now they also want the domain. What is the domain of the derivative? Anybody? So cool. That's right. It's going to be, the domain will be x greater than 0. X has to be greater than 0. We okay?
How did you get rid of the h when you went to like the 1 over like the radical? After you cancel it out, the two h's, but then there's like the 1 in the radical. Yeah, right there.
How I got the 1 or how I got rid of the h here?
How you got rid of the h? I see the 1 because it canceled.
What is this telling me to do?
Oh, plug it in.
It's the direct substitution. So I'm getting x plus 0 plus the square root of x. So that gives me the square root of x plus square root of x.
All right, cool,
Yeah.
got it.
Yep, no problem. So, see, God bless algebra, right? All right, let's add more algebra, because I know you guys love it. Right, Carol? All right. Now, in this problem, again, we're going to find the derivative. So again, the limit as h goes to 0 of f of x plus h minus f of x all over h is going to come into play, and you're going to see that this gets ugly quick. So I'm going to go the limit as h goes to 0 of 1 minus x plus h over 2 plus x plus h minus 1 minus x over 2 plus x all over h. What we end up finding out with these problems is that calculus is easy. It's algebra that sucks. The algebra is so tedious. All right, so in order to be able to do this problem effectively and well, we need to get a common denominator. And so I'm going to get 2 plus x times 1 minus x plus h minus 1 minus x times 2 plus x plus h all over h times 2 plus x plus h times 2 plus x, and that's going to be the limit as h goes to 0.
Instead of them on the top part of that fraction, that was just like the cross multiplying?
Correct. And then the denominator that's resulted ends up with the h in the far bottom denominator.
All right.
Is there any questions on how I got what I got? Okay, so all right, you guys are actually really, really strong, or not telling me the truth. I hope.
How did you get the problems that you did in step 2?
What do you mean?
Like how you just how it's over Just, I don't know, just like the whole equation in step 2.
This one?
No,
Or
it's
how I
the
got
one before
this?
that.
Okay.
That one, yeah.
So what happens here is, with this function notation here, correct? Everywhere I see x now, I'm going to put x plus h. So I'm going to go 1 minus, instead of x, I'm going to put x plus h. So that's how I got this. Then,
Okay, thank you.
that's enough? Okay.
Yeah.
Okay.
I had a
No,
question.
I think. Oh.
Go
You
ahead.
can go if it's cool.
Oh no, I just had a question for step 3. I'm confused on how you even got to that.
How I got from here to here?
Like the same denominator.
Okay.
The third step.
Here.
Yeah.
Okay. So to do this, all I did was, since these are fractions, right? They don't have common denominators. I need to create a common denominator. So to create the common denominator, this denominator needs to multiply with this denominator, correct?
Mm-hmm.
So once they multiply, in order for this to have the right denominator, this numerator needs to multiply with this denominator. And then this numerator needs to multiply with this denominator. So you can see the 1 minus x plus h, it's right here, is multiplied with this 2 plus x. And then the 1 minus x is multiplied with the 2 plus x plus h, which is this piece. Now, when these two multiply, that's this piece, and then the h that's on the bottom comes into play.
Okay, got it.
Does that
Thank
make
you.
sense? Do you want me to show
Yeah.
every step? I could do it.
I mean, I don't know if it would help everyone else for like later, so that when we watch it.
Yeah, you should do it.
People were immediately like,
Yeah,
please.
just do it.
Okay. So cool, no problem. So what's going to happen is this. I'm going to end up with, and I'll do it in color for you. This has to multiply with this, right? So that's going to give me 1 minus x plus h times 2 plus x, right? Then we have a minus sign in between. And now I need to multiply this with this. So I'm going to get 1 minus x times 2 plus x plus h, right? And then the denominator for that is going to be the bottom two. So these two now need to multiply, right? So I'm going to get 2 plus x plus h times 2 plus x, all of that over h, right? But h we can think of as a fraction, h over 1. And what happens when we divide by a fraction? Do you guys know what we do when we divide by a fraction? We multiply by the reciprocal. So when we multiply by the reciprocal, what's going to happen is I'm going to get 1 times x plus h times 2 plus x minus 1 minus x times 2 plus x plus h, and then this guy but then that's going to be multiplied by 1 over h. And when you multiply by 1 over h, what you end up with is this. We okay? Let's be fair. I've been doing this math stuff for, 25 years. So I can do this in my sleep. So if there's something that I skip because I think, oh, it's something you should be able to do, please ask. I want to help you. And I want to make it as clear as possible for you. I've got too much experience that I think it's something you might know that you might not. So help me be a better teacher by asking questions, okay? Does that help you, Alyssa?
Yes, it does.
Okay. May I erase that now? Because I think I might need the. Maybe I won't need the space. We'll see. But if I need the space, I'll erase that piece. Okay. Now comes the crazy part, right? We're going to do expansion, and so the expansion here is just distributing. And so when we distribute, I'm going to get 2 minus 2x minus 2h plus x minus x squared plus xh minus, and I'll do this one over here, 2 plus x plus h minus 2x minus x squared minus xh all over. And I'm not going to mess with the denominator. I'm not going to change the denominator. I'm not going to expand it. Are we okay with the expansion that I did?
Yes.
Okay, cool. So then I'm just going to write it out so that the signs are all correct. So it's easy for me to see what needs to be eliminated. Okay. Looks like 2 can go. Looks like x can go. Looks like 2x can go. X squared can go. Pretty awesome. That looks like it, right?
Wait, shouldn't the first xh be negative?
Oh, yes. Thank you. This should be a minus xh right here. And then that means this can go. Okay? So then I'm going to get the limit as h goes to 0 of a minus 3h over h 2 plus x plus h times 2 plus x. The h's are going to cancel, so I'm going to get the limit as h goes to 0 of a negative 3 over 2 plus x plus h times x, 2 plus x, and that's going to give me a negative 3 over 2 plus x quantity squared. And that's my answer. How's that? Tedious.
So in the final step of finding the derivative, so do you like just get rid of h then?
So at this point I can do direct substitution, because if I plug in h as 0, 2 plus x, that is not going to be 0 in the denominator, so I can do a direct substitution.
So you just like pretend that h is 0 at the end?
Well, it's not pretend. This is telling me that it's going to be 0.
Oh, sorry.
Does that make sense?
Yeah.
Okay. Don't you guys love this? That's awesome. Nope. See, I think this is fun. Because it becomes this cumbersome puzzle. But I remember being a student and not enjoying it at all. Just the uncertainty of it all, right? Where, oh, am I going to make a mistake? But eventually you get to the point you get so comfortable with it, it's just second nature. This is what 2.8's homework is going to be like. So 2.8's homework is going to take a little bit of time. Okay? I'm sorry.
I have a question.
Yes.
How do you do the expansion that quickly? Because I still have to do like all the steps to do it.
You're saying from here to here?
Yes.
Well, here's the way I look at it. So I take the first term and I'm going to multiply it with everything in the second. So what I'm doing is, some people do a thing called FOIL. I think FOIL is crap. I actually think of everything in terms of distribution, going one way and the other. So with the distribution, I think the first term times the second product, and then the second term of the first product times the second product. So I'm going to go 2 times 1, which is 2. 2 times a negative x is a negative 2. 2 times h, a negative h, is going to give me that negative 2h. Then I'm going to go x times 1 is x. X times the negative x is the negative x squared. X times the negative h is that negative h, xh. And do you see how it just gets quick?
Mm-hmm.
Then the minus sign, then I'm going to go 1 times 2 is 2. 1 times x is x. 1 times h is h. And then negative x times 2 is a negative 2x. Negative x times x is a negative x squared. And negative x times h is a negative xh.
Oh, okay.
I'm just super deliberate about my distribution. So I'll show you this. I'm just going to write it over here so you guys can see. So the way you guys were taught stuff in your classes was your teacher probably did something like this, right? This times this, and then first, how did they do it? It's funny. First, inside, outside, last, something like that, right? The way I've always taught my students to do this is I go the first term times the second plus the second term in the first product times the second. And so you get 5x, 4x plus 20. And the reason this is helpful is when you end up doing factoring, this is how factoring actually works. You end up with middle terms. If you use FOIL, once you get to larger termed polynomials, it's easy to get confused. I don't know anyone in Oakland. Does that make sense?
Yes.
All right.
Because my mind always goes to FOIL. That's why I was like, how did you do that?
Yeah.
But now I see what you're doing.
Yeah, it's
I
just
had a question as
distribution. Yes.
I understand pretty much everything except the very first step. We have to plug it into like the derivative formula, like the limit of as h goes to 0 of f of x plus h minus f of x over h.
Plugging into this?
Yeah, I'm good in everything except like I get confused on like how to set up the problem.
No. You know what? Part of the problem is we don't do enough things in function notation, and so that becomes problematic, right? So if I gave you a function, and the function that we had in that case was, what was it? X.
It was 1 minus x
1
over
minus
2
x.
plus x.
Okay. Yeah. So 1 minus x over 2 plus x, right?
Yeah.
Okay. So the way you look at it is this. All that's happening here is this variable is this thing, right? So if I change the yellow thing to a 2, everything that's yellow there becomes a 2, right?
Yeah.
That's function notation. So if I change it to x plus h, everything here has to become x plus h. So now I'm going to have 1 minus x plus h over 2 plus x plus h. Make sense?
Yeah, I see it.
So that's the x plus h piece, and then minus x f of x, that's the original function, is
Yeah,
1
x.
minus x over 2 plus x all over
Okay.
h.
Okay, I'm good now.
Make
Got
sense?
Yep.
Yeah.
Thank you.
Cool. Yeah, that's why I even teach, when I teach at Rio, I would connect my iPad and use my this app to teach because of the color, because I do think it helps students see it. Oh, that's funny. Someone told me what the FOIL thing is. I don't even know it. That's how pathetic I think it is. First, outer, inner, last. Thanks, Jose. That's cool. Cool. But if you're comfortable with it and you're good with it, please go ahead and continue to use it. It's to your benefit. Whatever is going to help you be successful, right? Okay. Was everyone able to copy this one down? All right. I'm almost done. All right. So it says a function f is differentiable if a function f is differentiable at a, and a here is a number, okay? If f prime of a exists. So if the derivative exists. So it is differentiable on the open interval from a to b if it is differentiable at every number in the interval. So what we're trying to do here is demonstrate that if we have a function, it's going to be differentiable. And to be differentiable, there's some conditions that must hold true. It needs to be smooth and continuous to be differentiable. Smooth and continuous. If it's not smooth and continuous, that means we cannot differentiate. So I don't know how to stress it enough. Smooth and continuous. Okay? If there's any issues with how smooth it is or how continuous it is, we're going to run into problems with taking the derivative. Another thing to remember is that the derivative really is the slope of the tangent line. Okay? That's critical. And then there's this theorem, and here's the theorem. It says, if f is differentiable at some point a, then f is continuous at a. So this is critical. I can take the derivative at some point. If I can take the derivative at that point is continuous. Okay? The converse of this isn't true. Something that's continuous isn't necessarily differentiable. But if it's differentiable, it has to be continuous. Does that make sense?
Yes.
Okay. So I'll just show you some examples. So if I did something like this, that right there is most definitely continuous, correct? And I should draw it a little bit better. That's continuous, right? I never lifted my pencil. But this thing is not differentiable everywhere. So even though it's continuous, it's not differentiable. Okay? If we have something like this, well, hold on, I don't need that circle. See if I can get rid of the circle. This thing right here is continuous, but again, it's not differentiable at that corner because it's not smooth. This here is called this one's called a kink. This is called a corner, and then we also run into the issue of if it's discontinuous, it's not differentiable. So this example here is discontinuous, and because it's discontinuous, it's also not differentiable. Okay? And I basically just drew pictures for the next piece when it's not differentiable. Corners, kinks, discontinuous points, and vertical tangents. That's the one I didn't talk about. The vertical tangent is if I have something that looks like this, and it goes vertical, meaning the limit of that thing goes to infinity. And if the limit of it goes to infinity, what do we know about at that value of x?
An asymptote.
It's an asymptote. And if it's an asymptote, how can we differentiate an asymptote? It's impossible. Does that make sense?
What does like differentiable like mean? Because I'm just like lost.
Okay, so the differentiability is basically finding the slope of a curve at a specific point. Okay, so if we're given a function, any function curve, right? So if I gave you a curve that looked like this, and we've done it in class, we did a bunch of secant slopes, right? But if I want to find something, so let's say that this was just zoomed in, this was x squared, okay? If this is x squared, and I wanted to find what the tangent was here, 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 or here, they're all going to be different slopes for the specific tangent, correct?
Mm-hmm.
But if I find the derivative of this thing, and I know the derivative of this is 2x, I can find the slope at this point if I know what x is, at this point if I know what x is, at this point if I know what x is, at this point at any of these points I can find out what the slope is at those points by finding the derivative to the function. The derivative of the function helps me find the slopes at any point on the curve.
Okay.
Does that make sense?
Yeah.
All right. Cool. Okay. Last thing I want to talk about, and then we can go into a review for the exam, is what the derivatives represent. So if I'm giving a position function, and typically what we say is s of t is the position function. That's typically what we use in mathematics and in physics for position function. Okay? The first derivative of the position function will yield v of t, and v of t is the velocity function. Okay? Something important. The second derivative of the position function is equal to the first derivative of the velocity function, which will equal the acceleration function. So this ends up being acceleration. Okay? There's one more that's not often talked about. The third derivative of the position function, which is equal to the second derivative of the velocity function, which is equal to the derivative of the acceleration. So as something's moving, it's speeding up, and then something hits it. What does it do to a person's body? We call it a jerk. Now you guys can go up and you guys can wear a little badge that says don't be a triple derivative. Right? If you really want to be a nerd, there it is. The third derivative is if you started to run and someone hits you, you're going to go in a different direction all of a sudden, right? Because remember, acceleration, velocity, they are vectors. And so as you're going, if something changes your direction all of a sudden, that thing that changes your direction is a jerk. Yeah. Make sense?
Yes.
All right. That's 2.8. Not bad, right? Chapter 2 is done, guys. We've only got 4 more to go. No, it's not bad. Okay, do you guys want me to stop the recording here and then start a new one for the review?
Yes, please.
Yes, please.
Okay,
Yes,
let me stop this.